So we move on to start discussing the concept of ordinals, and they are built out of these well-ordered sets, and in a lot of ways they're kind of the same thing as the natural numbers that we described earlier, but we define them in a through a slightly different path. It'll turn out that every natural number is an ordinal. The converse is not necessarily true, but so there is a difference and a distinction, but there's also a lot of overlap. So to begin with, if two well-ordered sets are isomorphic, then we say that they have the same order type. And then we'll go on to say what it is to have an ordinal. So intuitively, what we want out of an ordinal is that one is less than the other if and only if inclusion holds in that order, and also transitivity. This is going to give us a way of always being able to use set theory to define the ordering relation on these things and ensure that every two things are comparable and so on. Formally, the way that we define an ordinal number is anything that is transitive. Recall that means inclusion implies being a subset, and that it be well-ordered by inclusion. This, essentially gets us the first two properties of a partial ordering, and in fact, it'll be some work to show it, but it'll actually, on the class of ordinals, it'll even give us the third property, therefore making this a linear ordering. Now, just a comment that n itself, the set of all natural numbers as well as every individual natural number, is an example of an ordinal, but we'll eventually see other examples as well. Just as a comment, it may seem like the empty set would not be an ordinal because it doesn't seem to have a least element. In fact, it doesn't have any elements, but at least that was my initial confusion, and that's why I sort of air it in case it's anybody else's initial confusion. But in fact, it is an ordinal because we don't require that every ordinal have a least element per se. We require that every non-empty subset have a least element, and since that'll just hold for the empty set by trivial quantification. So that is the end of that comment. Okay. We will prove this theorem in the next video.